All right, moving on. Let's look at this next polynomial function. It says consider the polynomial function f of x equal to 2x to the fourth power minus 8x squared. Well, right off the bat, let's go ahead and talk about this polynomial. It's in standard form. We've got our leading term up front leading the polynomial. Our term with the greatest power is called our leading term, which in this problem is 2x to the fourth power, right? That's our degree 4 term. So our leading coefficient, let's go ahead and answer the leading coefficient for this problem. Leading coefficient would be 2, right? So leading that polynomial. And the degree being the exponent from the leading term, our greatest power in this polynomial, is a degree 4 polynomial, which implies what? 4 linear factors. Degree n polynomial has n linear factors. So we do want to factor it, but right now let's go ahead and state the leading term here, which is 2x to the fourth power. Right? So while we're at it, let's go ahead and factor this polynomial, and then we'll continue on with the next few questions. This one's easy to factor in that we have 2 terms, right? And in both of these terms, I see a GCF, right? A greatest common factor. All right, with 2 and 8, we got a common factor of 2. And with x to the fourth power and x squared, we have a common factor of x squared. So let's bring out that GCF, right, of 2x squared. So as we do that, as we bring that out, right, we'd be left with 2x squared. With x squared, right? 2x squared times x squared is 2x to the 4th. And then in the second term, as we factor out the GCF of 2x squared, we'll be left with a 4, right? 2x squared minus 4 is minus 8x squared. So we're getting somewhere. We're trying to get down to our 4 linear factors. So now we're down to 2 quadratic factors. Now these 2 quadratic factors can easily factor. This x squared term, for example, is x times x. And x squared minus 4, and that's a difference of squares, right? We got a difference of squares here, so I'll make that note. Difference of squares. So with the difference of squares, a squared minus b squared, that factors to a minus b times a plus b. So x squared minus 4, which is x squared minus 2 squared, factors to x minus 2 times x plus 2. And there are your 4 linear factors. We got 2 of the factors of x times x, and x minus 2 times x plus 2. All right, moving on, let's start to get into the characteristics of the graph. It says determine the end behavior of the graph. So remember, the end behavior goes off the leading term. So the leading term, again, is 2x to the fourth power. So that implies we have a leading coefficient. All right, go ahead and write that down. Our leading coefficient is 2. So it's greater than 0. And our degree of the polynomial is 4. So that implies we have a even degree. So with a even degree and a positive leading coefficient, the ends of our graph go the same direction, and they both go to positive infinity. So left-tailed infinity, right-tailed infinity. That's with a positive coefficient, so leading coefficient greater than 0 and even degree. That's true for all even degree polynomials with a leading coefficient is positive. So left tail and right tail. So in the middle, now again, I don't know what's happening in the middle. It could have turning points. And speaking of the turning points, we know the maximum number it can have. So remember, based off the degree of our polynomial, so if the degree is equal to 4, that implies at most, right, 3 turning points. And again, what are your turning points? Your relative min and relative max points, right? Those are our turning points, where our graph turns or changes in behavior, right, from increasing to decreasing or decreasing to increasing. So we can have up 3 turning points between the ends of that graph. Find the domain. Now we know that the domain of this function, domain of all polynomial functions, is all real numbers x. There's no undefined values, right, in a polynomial function. Range will be restricted in this one with the even degree. It'll be based off our minimum point. All right, this graph has ends that both go up. So with that said, we'll need to find the min value, and it goes to infinity if we want to talk about the range. Let's find the real zeros of the function and state their multiplicity. All right, so remember, with multiplicity, it tells us the behavior of the graph at the x-axis. It tells us if it crosses through the x-axis at 0, if we have a odd multiplicity, or it touches and bounces off towards a turning point at 0 if it's an even multiplicity. So since we factored it, all right, let's go ahead and write our factors back down here. Let's go back here, bring that back up, and get back to our problem. So remember, we've got our factors here, so I'm going to write them back down. So again, f of x. Yeah, I like to write it in factored form because that'll make it easy to see the zeros and the multiplicity. X times x minus 2 times x plus 2. All right, so that implies our zeros, which again are the locations of our x-intercepts, and our multiplicity, which is the number of times that 0 occurs in your factorization. So we know with x, right, that factor, we know with x, we're talking about the 0, we know that x equals 0. And we know its multiplicity, right, on that would be 2, right, because it's used 2 times, right? That factor is used twice. Number of times that factor occurs is the multiplicity. Now, with that said, it's even multiplicity. So that implies our x-intercept, which is 0, 0, right, crosses through that point. If it's odd, touches if it's even. So let's go ahead and write down there. So it'll touch. It touches at 0, 0. All right, let's move to the next factor that we had here. When we write this in a different color, we got x minus 2. Well, we talk about the 0, x minus 2 equals 0, and x equal 2. And again, it's multiplicity. Write down the multiplicity. The number of times you see that factor, well, its multiplicity is 1. So again, it's only used one time, right? It's factor. So you only see one of the factor of x minus 2. So again, that defines our multiplicity. So this time we have an odd multiplicity. So with that, since we have a odd multiplicity, that implies it crosses through. 2, 0, right? And now let's go to our third and final 0, the real number 0. We got x plus 2. So we're looking at the zeros. X plus 2 is equal to 0 when x equal negative 2. So there's 0. So we got a 0 here, which again is the location of our x-intercept, negative 2. And our multiplicity, number of times that factor is used is once. We only have one of the x plus 2 factors. So again, we have a odd multiplicity. So that implies touches or crosses. Well, odd, it crosses through. Crosses at negative 2, 0. So let's go ahead and write those pieces of information here on our graph. So again, we got a 0 at negative 2. And I'm going to go ahead and plot negative 2 over here. We got what? Negative 2, 0, and 2. So here's negative 2. Here's our multiplicity again. We can put them in that color blue if you want. Here's 0. And then we've got 2. So we write it in there. Let's put that in black. So that's what we had that one in. 0. And then at 2, we'll put that one in blue. So there again, there are the 3 zeros. And we know the behavior now based off their multiplicities. What happens at those locations. So remember our leading term test. Left tail and right tail go to infinity. And at -2 and at +2, since we have odd multiplicity, it crosses through at those locations, and at 0 it touches. So as we look at our left tail, coming from what? Infinity. Right? And then we go back, of course, we know it's going to touch here at 0, not cross through. So it's tangent and forms a turning point at that location. And then it's back up and crosses through at 2. And goes all the way to infinity. And why do we know that? From the leading term test. So again, even degree polynomial, right? Left tail and the right tail go to infinity. But now we know the middle behavior, right? We know what happens in the middle. We have one turning point. That turning point's at the origin. So there's our graph, our sketch of this function based off that information. So you can see, using the leading term, using your zeros of multiplicity, we can build a quick sketch of our polynomial functions. Now, moving on, let's go ahead and talk about a set of x values for where f of x is greater than 0. So where is this function greater than 0? Where is it sitting above the x-axis, right? So greater than 0 right here, right? Greater than 0 over here. So you can see our graph here on the positive side of the y-axis. So we're looking at greater than, so we're looking from what? -infinity. And here, they're all greater than 0. So all x values that are less than -2, so -infinity to -2 is greater than. They don't include -2. At -2, it's equal to 0. And then also from what? 2 to infinity, it's greater than 0. So between 0 and 2, it's less than 0. So again, as we started in our second interval, all x values greater than 2. So there are the two intervals. On what set of x values f of x less than or equal to 0? We can write those down. Put it in a different color. In here, right, we're less than 0. We're less than 0. So again, as you're looking at that interval, right, I'll highlight it. So let's write in those two. So greater than -2, now it wants to know equal to here, so we need to include -2. So all x values greater than or equal to -2 and less than or equal to 0. Well, since we're including that, that goes all the way over to 2, so we don't need to separate it. So go all values greater than or equal to -2 and less than or equal to +2. There's our set of x values for this function is either less than 0 or, of course, here it equals 0. So again, there's those function values. So again, that's analyzing a polynomial, right? By using its sketch, its graph. With that said, you can move on to our next topic. We'll do that here in a second. We'll stop there with that one. Take a quick break.